Sorry, I was muted. All right, let's start. Welcome to the Graphics Programming Virtual Meetup. Today we will continue talking about how to build a BVH. Wait, this is a link. Okay, so top level acceleration data structure and bottom level acceleration data structure. So yeah, we will explore how to build a BVH for a fully dynamic scene using the same techniques employed by modern games, namely top level acceleration structure and bottom level. I don't know how to pronounce that. Like mass and place. It's French, so
Mise en place, I think.
Yeah,
yes, yeah.
Is my audio working now? Is that?
Yep, we can hear you.
Okay, cool. Good. Yeah, mise en place is like preparation stuff, preparing ingredients, things like that.
So we need multiple BVHs. Add a BVH class to encapsulate the BVH node pool, triangle indices, and triangle list. Yes. So we just move a bunch of free functions and data into this class. Build BVH become BVH build refit. Yeah, that makes sense.
So we're kind of setting up some encapsulation, I guess, is the idea. Right.
Yeah, just basically encapsulate a bunch of stuff into this. I don't know. I don't even work. Like encapsulation alone, I won't even call it OOP, but yeah, whatever. I just feel like that's just normal stuff people do. Even without OOP, there are other ways to do encapsulation. Like in C, people also do that all the time. Yeah, anyway. So yeah, so since we have a class, then we can have multiple copies of BVH easily, just create another object. And yeah, both will be at the same location. We could solve this by adding offset to the vertices. Next issue is to the calculation of the intersection. We can just call this function once for each object. Then that does work, but it seems impractical for things with a large number of those entities. Yeah, also why do we store them twice when it's the same polygon? So we can just use instancing. So start with the last question to move something. Yeah, we can add a translation to every vertex in the mesh, which is not practical at all, but instead we can just inverse transform the camera, which is what we so-called the view matrix would usually do. Oh, here's a comment that the public interface looks like Vulkan's. Yeah, I guess that's probably how some of the inspiration of his stuff. And nice to see connections.
So what he's doing there is, yeah, he's just changing the ray origin when he's doing the second copy of it.
Yeah. Yeah, so basically, yeah, change the ray origin and intersect again. So to like same BVH is the intersect twice with a different ray origin. And moving the ray of opposite direction of mesh can be applied to translations as well as orientation. Yeah.
That's very neat.
Yeah, basically we just use a 4x4 matrix. This may sound complex. I guess this is for people just doing ray tracing, because for people doing like real-time rendering, this is just what we do all the time. Yeah, they still work if the matrix changes from one frame to another. Because yeah, mesh motion defined by a matrix does not require rebuild or refit. And it's essentially free. And for spinning, so we store a transformation matrix and we store a bound of BVH in word space. Wait, they store them directly in BVH? That is bad OOP, to be honest, because those things, I think it depends on different instances.
No, I think what they're doing is this is the transformed model. So when you transform the existing
Yeah, I
bounding
know, but they probably just set transform every time.
Hmm.
But I think this is not a good practice. They should be separate. Yeah, calculate inverse transform and then calculate the bound by there. I don't know, like, feel like sometimes he feels something is easy, I feel it's not, but for this, it's just opposite. Using invert transform, we can make a we can modify the BVH traverse by transform the position vector. The methods note the reorigin is a position. To transform it using a matrix, we should apply rotation and translation. We thus use a homogeneous coordinates with one for for direction. On the other hand, we use homogeneous coordinates with 0 for W. Yeah, just for a refresher, when we homogeneous coordinates is 1, when we multiply by 4x4 matrix, it will actually add the translation, like that columns for translation will be added. If we have 0, then that column of translation will just be ignored. That's how it works. At the end code, we restore the original array, except for one field, the t value. So this array. Where do we restore the original array? don't see it.
I think it's done internal to the intersect function.
Oh, oh, okay. I see. That's why I definitely don't like this architecture. Like, this should just be outside of the BVH logic, and then you don't need to do that inside BVH. Instead, you should do that outside, and also the original ray should not be changed. You should just transform the ray to a new ray and then pass it into the BVH. At least that's how I would do it. Yeah, what if we have a lot of those? That's why we need top level acceleration structures. Yeah, a pair of BVH can be combined into a single BVH. Add a new node. And yeah, we can just keep adding. So yeah, top level node, which yeah, it looks like a regular BVH node. Yeah, the
Okay.
tricount field is not needed anymore. So we still need to know if it's a leaf node or not. Then we will just use an int. And yeah, we get a top level acceleration data structure as a class, which has a bunch of similar things. Triangle array of BVH is replaced by a BVH array.
Yeah, it makes sense. So instead of triangles, it's full modeled. Yeah.
Yeah. Yeah, let's build a minimal top level, which is just list and aligned alloc. Oh, why they need aligned alloc when this is already oh, anyway. And node used. I feel like on GPU, probably aligned malloc can be helpful. On CPU, it probably doesn't matter. For just 2 BVHs, we can build it manually. Like 2 and 3 is leaves. And the root node over a 2-leaf node. Those min and max is some really large number. I guess they will fix that later.
Yeah, I think it's kind of arbitrary. Yeah.
Yeah. Also, why they don't skip 1? I think he may talked about it before, but I forget why he skipped 1.
Yeah, it was something to do with padding, I think. I don't remember exactly.
Yeah. Yeah, root has a massive AABB for now. Yeah, they'll fix it later. Yeah, traversal is the same kind of deal. Yeah, difference between top level and bottom level is the leaf node. Yeah. Put that into test first to create a init function, which just loads the 2BVH, which is actually redundant, but whatever. Yeah, we can just do this. We now have, 2 BVHs as like this. Loose end. Yeah, because we don't know how to rebuild the top level per frame. We build a top level BVH with a lot of objects. Because instancing, especially, this, I guess that's what my complaint with this is. This clearly doesn't work with instancing. Just they need to fix that. And proper AABBs. Otherwise, now currently this AABB is just useless. Basically, we get even slower result. And instancing and also refitting and rebuilding.
If they both reference the same triangle list, like, well, isn't the transform and the bounds, well, the transform and then the transformed bounds, I guess, would be the stuff that's unique to each instance.
Yeah,
Copy.
that can work, but just that feels super weird. So yeah, it can work this way. Do we want to talk about the next article or just stop here?
We can do the next one, yeah, sure.
Let's see how long it is. It's not very long. So yeah, let's start. Yeah, the conclusion for the previous article just is underwhelming because of a lot of things. And the goal of today is to have 256 objects while rotating and bouncing off the walls of a virtual cube. Total polygon count will be 30,000 times 256, so 7 million triangles. And to build an optimal top-level acceleration data structure, the pairs that we create must be carefully chosen. Yeah, we should be pairing nodes that form small boxes. But do we actually use surface area heuristic for this? Because this feels like expensive per frame. Yeah. The O(n) square algorithm. Then this algorithm only get us one pair, and we need more pairs, the O(n) cube. So it's definitely not what we should do. There's a 208 paper titled Fast Agglomerative Clustering for Rendering. The term agglomerative clustering refers to the bottom-up process we use when we combine pair of nodes. Yeah. The alternative is the top-down process we use for constructing bottom level. The algorithm from the paper in pseudocode is get the first one, then find the best match for the first one, then for a while loop, find the best match for the second one. If they are equal, then we pop both and say it's a match. And add a new parent node. And then repeat this process. Otherwise, A equal to B, B equal to C. Otherwise, also repeat this process, but just discard A, basically. He really don't like curly braces, and he likes comma operator. Performance is, yeah, we get O n square in practice. For 256 object, yeah, it works. Yeah, before we turn that into, we need to change the struct before. The struct store only the index of left child. Assume that the right child can be derived from that. But using agglomerative clustering, that's no longer the case. We just do that. 16 bits, so we assume that the top level node will contain no greater than like 30,000 objects, which in our case it is. So yeah. Oh, I guess it's 60,000 because it's unsigned.
Yeah, interesting.
Yeah, for leaf nodes, field BLAS store the index of a BLAS, otherwise it's unused. Back to the top level construction. Construction start with the 256 leaf node. Nodes used as one, and then for each BLAS, we just calculate the bounds and make it a leaf. Now we have a leaf node, we can create a work list for agglomerative clustering algorithm, which is node indices. They just hard coded to 256. I really don't like that, but yeah, whatever.
I'm not really understanding the motivation for building this hierarchy in a different way.
It must be faster because it needs to be rebuilt per frame.
Is it okay? Maybe, yeah.
Yeah, it's useful for when you want to have instances of objects that move without having to update every vertex. That's what the ray tracing APIs do. And by that I mean the Vulkan ray tracing and DirectX ray tracing.
I think I just reread that BVH survey paper a long time ago that it talk about the merit of top-down and bottom-up approaches, that there are just a lot of different approaches, but I can't remember a thing from that paper now.
Yeah, I need to review that one too. Yeah.
Yeah, I need to review that one. Everything is now ready for actual clustering, and the algorithm called find best match 3 times. We'll find best match is algorithm that just loop through all the node and find the best match. Yeah. With that find best match function properly implemented, we can now finalize the agglomerative clustering algorithm. Yeah, which is just pseudocode we've seen before. You when two nodes are paired, work item A gets replaced by the index of a newly created interior node. And work item B, which is to be removed, get replaced by the last item in the list. And the list is shortened by 1. Yeah. So yeah, let's create 16 of the BVHs and then create a top level. Yeah, building BVH for each of them is redundant and takes a lot of time. And we can create some animations for just perform some animation for them. Depend on those like X and Y.
Very readable.
Yeah. Yeah, it's super ugly code, yeah. That's shitty toy kind of stuff, so understandable. Yeah, changing the transforms of the BVH is update their wood space bound, so we need to build a new top level. Then yeah, we need to just rebuild the memory frame, and that's it. We can also tilt and move the camera a bit. Oh, they can still run 60 frames per second. Nice. So yeah, for more object, we really need instancing now. Yeah, instancing helps to reduce memory use and bandwidth between CPU and GPU. Plus, one more, we can reuse a BLAS if the only difference between the two objects can be expressed in a matrix. Sorry, I have a phone call. Can someone take over?
Sure. Yeah. Okay. Okay, so we've got okay, more French, I guess. We've got all right. So looking at doing instancing now, we've got just a couple of trees that are copied all over, slightly different scale and orientation to prevent the repetition. So instancing is for reducing memory use and bandwidth. In Ray Tracer, we're getting the same benefits plus another one. We can reuse the BLAS if the only difference between two is the 4x4 matrix transform. So on a racetrack, one car gets multiplied to form a grid, add a track, and then you're done. You have different textures based on which instance it is. Since the materials are not, they don't affect the BVH. So making the necessary changes, got an instance class. And so we've got a transform and then a pointer to a BVH for that. And then also bounds associated with that instance. We've got a inverse transform and world space are now gone. ray transforms handled by short method BVH instance forwards the work, already transform ray into the BVH. So now instead of operating on BVHs, we're operating on BVH instances. The TLAS constructor takes a BVH instance array and creating creating a list. Also means that member bits or member variable BLAS is now BVH instance rather than a BVH pointer. Yeah. Apart from this, for a few changes, there's so creating 16 instances, then creating TLAS from the list, 16 entries. We're in the army now. 256 armadillos rotating and bouncing off the walls. Putting them in random positions with random orientations. Okay. Okay, and then using that to update the transforms. 8.5 million rays per second, 7.68 million triangles. And updating the TLAS only takes half a millisecond. Neat. For BVH maintenance, we can add functionality like refitting for meshes that deform, still instance them complete with animation. Adding rebuilding for meshes that undergo more structural changes. Move large static meshes by changing their transforms only. Add all this in a single framework that intelligently divides the work over frames for an optimal balance between ray tracing speed and BVH maintenance time. In terms of performance, we only scratch the surface can, for example, trace bundles of rays to greatly speed up the kind of ray distributions we use in these demos, exploiting the fact that the rays for nearby pixels tend to travel in the same route through a BVH. We can also build a BVH more than 2 child nodes per level to reduce the number of traversal steps. Beneficial for rays that go all over the place, like those in path tracing. There are fewer levels of indirection there, I guess, yeah. Then there's the actual using of the rays. So we've done only grayscale images based on depth. Doing that for animated, yeah, okay. Doing photorealistic rendered images for animated scenes is a good thing. That's what we're looking for. Cool.